All right, so welcome back to another lecture on safety and systems programming. Thanks for sticking with us. Some quick logistics just to start out. Everyone make sure that you're on Slack. So if you're not on Slack and you need help getting on Slack, stick around afterwards and I'd love to help. If you're officially signed up for the class, you should have access to Canvas. And then if you go to the Slack tab on Canvas, you can join through Canvas. If you don't have access to Canvas or you need help or anything, something's wrong, just let me know and we can work that out. But we're going to be sending most announcements through Slack. So if you need help getting on, then definitely let us know. Also in the Slack general channel, we sent out, and also through email, we sent out the link to the intro survey. So I think the majority of people have filled it out, but if you haven't filled it out already, please do so. We would love to hear from you. In terms of out of class work, we'll have the first set of exercises and survey coming out today, and that'll be due next Thursday. So these exercises should be pretty short. We're going to be talking about a lot of different code analysis tools in lecture today that do different things, and in the exercises we're just going to have you run them so that you know how to run them and maybe get a sense of what their limitations are, what they can and can't do. Every week we'll be giving out a really short survey. We just want to see how you're doing in life, how you're doing in the class, and if there's anything that we could be doing better. This is the second time we're teaching this class, and so there is still a lot of improvement to be made. We'd love to hear what you find interesting, what you find maybe not so interesting, and this survey feedback is really, really important to us. So if you can just take like 3 minutes to fill that out, we would really, really appreciate that. And then just a quick reminder, if you are able to turn on your video, that does help me a lot during lecture. So today we are going to be focusing on what we can do to improve the quality of our C and C++ code. Last class we saw that it's actually extremely hard to write correct C and C++ code. There are just so many different kinds of mistakes that you can make. Some of them you can look at it and you can be like, oh yeah, that's definitely buggy. And some of them you can look at it and you can be like, that looks right to me, until you look at it hard enough and actually there's some very, very subtle mistake that ends up causing very serious issues. So this is not a new problem. C has been around since the 60s, and it's not a new language. It's had these challenges for a long time, and so over time people have been developing tools that help us find these kinds of mistakes and make less of them. So we'll talk about C and C++ land today, like what can we do to improve the situation, but as we'll find, it's not perfect, and the best that we can do is not quite good enough. So this will help motivate why we care about Rust. Rust is actually a pretty difficult language to learn, and it can be a pain in the butt to program in it sometimes. And I really want you to feel like you understand why we're taking that effort when it's not, maybe not super straightforward. So that's today. And then next week, Julio is going to be lecturing, talking about well, how do other languages, like why do we have these other languages and how do they work and how do they address some of these shortcomings? So we started last class talking about how do we find...
We have a quick early question. Do
Yeah,
we
what's
have
up?
any use cases for writing in C and C++ today, given all these concerns that you're bringing up?
Absolutely. So let's see if there's time at the end of lecture and maybe I can talk to that, or maybe we can talk about it next week, because it might be easier to answer that question once you have more things to compare to. So last class we talked about how there's kind of two categories of techniques. You can either run the program and see what it does, and we call this dynamic analysis, or you can just read the source code and see if you can spot any bugs without running the program. So let's talk about dynamic analysis first, and then we'll talk about static analysis. So you're all familiar with dynamic analysis already because you've run... actually, I shouldn't assume this because I don't think 107E mentions Valgrind. If you took 107, You've probably seen Valgrind run before, where you write some code and then you run it through Valgrind, and Valgrind tells you if you have like out of bounds accesses or like use after freeze, or you're using uninitialized memory or something like that. So Valgrind, the way that Valgrind works, Valgrind is actually a pretty old tool, but it uses some very, very, very clever strategies. What it does is Valgrind takes a compiled binary. So first you run your code through like GCC or Clang or whatever compiler you're using. That generates a binary. So the binary is made of assembly code. And then you run this binary under Valgrind. And what Valgrind does is it actually patches this assembly on the fly. Like it's modifying this code that you're executing as you're executing it. So like it will replace this call to malloc. We have a call to malloc here, which gets compiled into a call to malloc with argument 8. It actually replaces this call with a call to its own version of malloc so that it can observe all of the allocations that you make. It can tell if you pass like a bad argument here, and it'll keep track of every time you allocate heap memory, so it knows where all your heap allocations are. And it will also insert additional assembly instructions every time that you have a load or a store. Every time you write or read memory, it will keep track of those memory accesses so that when you actually go to run this assembly code, okay, you allocate some memory, that's cool. You store the pointer in the returned pointer in memory. So there's a memory write, that's cool. There's a memory read here, that's fine. We haven't done anything bad yet. And then this last line here, I should point things out in this code. We're allocating a buffer of size 8, and then we're writing to the index 16, which is obviously out of bounds. And so Valgrind should complain about this. And what it does is it goes through all of this, and then we get to this last one here. And it says, hey, invalid write of size 4. I observed all of the memory allocations that you made in the heap. I kept track of everything that you allocated. I see you writing to an address here that is inside of the heap, but it's not inside of any heap allocation that we made. That's not legit. That's probably out of bounds of some access that you made. And so it gives you like this cryptic error message, hey, invalid write of size 4. And then it's kind of on you to go back through your code and try to figure out, okay, where is this write happening? What is it writing to? How did I end up with some sort of buffer overrun here or something like that? Okay. Yeah. So you compile the program first in a normal compiler. So this stuff on the left happens regardless of whether or not you're running Valgrind. Then you take the compiled program and you give that to Valgrind. Valgrind does not actually read your source code. It doesn't know anything about your source code. It just sees the compiled assembly. And Valgrind kind of modifies this assembly on the fly and runs it. So it's not necessarily like helping you understand the assembly. Most of the time it doesn't expose this assembly to you. It's just so that, remember, what is dynamic analysis? You're trying to run the program and watch what it does so that you can see when it does something bad, right? If we just, you can actually try compiling this and running it, and it probably won't crash. It probably doesn't segfault. It did something bad. It wrote out of bounds of this buffer, but just because of the way that memory gets laid out, there's some extra padding here. You overwrote a random byte in the heap. Probabilistically, it won't make your program crash, even though it did corrupt memory, and this is very not good. So the point of modifying this assembly is so that Valgrind can observe all of the things that we're doing, so that it can observe, okay, you're calling malloc. It can observe, okay, you're loading and storing memory. And then every time you load and store memory, it can validate what you're doing and say, okay, that's legit. That's legit. Looks like you're accessing a pointer here that's not inside of any heap allocation that we made. That's probably not so good. And then it prints an error message saying, hey, invalid write of size 4. You've probably seen some cryptic error messages like this. Any other questions about this? So I mentioned Valgrind's a pretty old tool. It's been used for a really long time, and it works pretty well. One of the most amazing things about this is it works with any binary compiled by any compiler, even if you don't have the source code available. So sometimes security professionals will use tools such as these in environments where they're trying to find holes in a system and they may not have the original source code available. This is actually quite common in like very large corporations. Sometimes people don't do the best job of keeping track of source code, and sometimes the source code even gets lost. I think this happened with MS Paint, where Microsoft needed to make a like critical. I don't think it was Paint. I don't know why you have a security vulnerability in Paint, but there was some. I'll find it and I'll send it in Slack. There was some Windows program that needed a critical security update, but the only problem was they lost the source code. And so they needed to figure out how to update the program without the source code. And they did some fancy stuff where they like decompiled the program and then patched it and then recompiled it. Crazy stuff. And this happens sometimes. Sometimes you don't have source code available and you need to do some analysis, see if things are working okay, find some bugs and whatnot. So this is very, very helpful. But the downside is that there's not a lot of information inside of binaries. Imagine what it looks like. I don't know how many of you have looked at assembly that is touching variables on the stack, but when you have local variables inside of a function, at the beginning of the function, what it does is it just like pushes the stack pointer down. It basically just allocates some memory on the stack. And then every time you work with those variables, it just like reads and writes to various places in the stack. If you look at the assembly, there are no variable names. It doesn't say, oh, you're using this integer of size 4 at this place on the stack. If you allocate a stack buffer of size 128, there's nothing in the assembly that says, oh, this is a stack buffer of size 128. It just like moves the stack pointer down and makes a bunch of room. And then there are 128 bytes somewhere in there that happen to be your buffer. But it's not specified in the binary like, oh, this is a buffer here. And as a result, Valgrind actually has no idea where your stack variables are. And if you have, so it's pretty good at detecting heap-based buffer overflows because it replaces every malloc call to its own allocator, and then it knows where all your allocations are. This is kind of how it knows where the variables are, because it's like, okay, well, you made this allocation of size 8, you made this allocation of size 32. I'm going to make sure that like if you use heap memory, you're within one of these allocations. But it has no idea where your stack variables are. And so if you have a stack-based buffer overflow, I think I have a, no, I don't. I didn't have an example code. I do on the next slide. Valgrind won't tell you. It has no clue that you wrote past the end of the array. This is one reason why, like in CS 107 and 110, you can get comments on your style grading, say like, you have a buffer overflow here. And you're like, wait, but I ran it through Valgrind. And Valgrind said I didn't have any buffer overflows. And it's like, yeah, well, Valgrind can't see everything. It doesn't really have that much information. So there are next generation tools called sanitizers, which I think everyone should be using instead if you can. It's the same idea, but instead of instrumenting the assembly, by the way, instrumenting means like hooking in and modifying so you can kind of see what's going on. Instead of instrumenting the assembly, you're instrumenting the source code. I'm approximating here. It does some fun transformations before it does instrumentation, but we won't talk about the specifics. But if you have code like this, which is a stack-based buffer overflow. So here we're allocating some memory on the stack, size 8, and we're going past that. There's no information in the assembly that will say, oh, you have a buffer of size 8 here. And so Valgrind will miss this completely. But if you do this with LLVM, because it's instrumenting the source code, it can actually see in the source code, you are creating a stack buffer here. And so it will insert some extra code into your program saying, hey, make a note somewhere that this program has a buffer called buff of size 8. And then every time you access memory, it will insert some extra code saying, hey, make a note somewhere that we accessed this buffer at this location. And then it can realize like, wait a second, that's not legit. This is really nice because it can see more mistakes. It has more information available. It's easier to implement. And so there are more kinds of sanitizers available just because people feel better writing them. And also the error messages tend to be a little nicer because it actually like knows what your variable names are and it knows more information, whereas a lot of that information is lost by the time that it's compiled to an actual executable. So there are a bunch of different sanitizers. these three are kind of like the three that you're used to seeing from Valgrind. So address sanitizer finds like out of bounds accesses. Leak sanitizer finds memory leaks where you fail to free some memory. Memory sanitizer finds cases where you're using memory but you haven't initialized it yet. But there are also other ones. So there's this thing called like undefined behavior sanitizer. Last time I showed this like very subtle buffer overflow that was caused by an integer overflow, where you are converting between like signed and unsigned integers. And that's the sort of thing that you can detect here. We haven't talked about threads yet. That's something that we'll cover in the last half of 110. But multi-threaded programming is very difficult. It's very easy to mess up. And there's a thread sanitizer that finds when you're using threads incorrectly. So like remember this, and I'll actually come back to this when we start talking about threads so that you can run this on your CS110 assignments. Any questions about like what this is or what it does or what the idea is here? Again, in the exercises, we'll have you just try running these tools so that you kind of know how they work. And then if you want, you can run them in 110 and try to maybe see if they catch any mistakes that you missed. Okay, so cool. Let's, I see the question, and that's actually the question that I'm about to ask, which is, are sanitizers going to find all the issues? Like, cool, let's sanitize all the code. We'll just find all the bugs. What's the problem here? Like, why doesn't everyone just run sanitizers? How come you haven't heard of these magic tools before? Why don't we just run these and fix all the bugs? Yes, exactly. And it turns out that this is a fundamental limitation of the strategy of dynamic analysis, which is run the program and watch what it does and look for when it does bad things. You can only see it do bad things when it actually does bad things, right? If a program runs fine with the input you provided, but maybe there's some malformed input, some like weird edge cases where if you put just the right input, then it does something bad. Dynamic analysis can't tell you anything about that. And if you think about the code example with getS that we gave last lecture, we're allocating a buffer, we're reading into this buffer, and we're just converting it to uppercase and printing out the result. And this works totally fine. Like dynamic analyzers won't complain about this at all, as long as the test input that you use is shorter than 100 characters. As it probably will be, because you're probably not going to want to type out a really long string on your terminal when you're testing this. And then some other clever attacker will come along and will be like, hey, I wonder if they handle really long strings. And so then they'll put this weird edge case in, and all of a sudden your program will fail there. And you won't realize it because you didn't test that. And how do we find these weird edge cases? It can be really hard to think about, because when you're programming a program, you are thinking about how should my program work? How should it work? You're not quite thinking about how should it not work? Like what should it not do, at least most of the time. And that's what a hacker or an attacker is trying to do, is they're trying to say, okay, how do I take this well-intentioned program and twist it to make it do something that it was not intended to do? How do I give some completely malformed input that nobody would have thought of in order to take control of this program and make it do something really bad? That's what happens, and it's really hard to think of like, okay, how could I mess up? If it's something this simple, then you can just know, okay, well, I can put a long string, but most of the time it's not this simple. So how do we find weird edge cases? Can anyone think of any fun strategies? If you actually know the answer to this, like if you've worked with these tools before, then hold that thought for a second. But for those who have never seen this problem before, how would you solve this? Yeah, that's a really good idea. We can just like, I don't know, take a random string generator and generate a bunch of random inputs and like see if we can make it crash. That sounds great. Any other comments or thoughts, or maybe why that might not work so well? Sure, absolutely. So one of the arguments of open source software is more eyeballs, more crazy things that people can come up with. Somebody else will think of like, oh, what if we try this? And absolutely, that has certainly helped in the past. Ryan, did you have a comment? It's not guaranteed to find any issues. But even worse, it's actually very unlikely to find many issues at all, just because your search space is so large. Like if you can imagine there being countless possible inputs, let's just say millions, even though it's actually way more. Like we don't have a name for how many inputs there are. Imagine that there are countless inputs that can cause problems, and there's only a tiny subset of them that will actually cause crashes. I'm sorry, there's a ton of possible inputs that you can give to your program, and only a tiny subset that cause crashes. If you're just throwing darts like at a board randomly, it's very unlikely that you're going to find that tiny subset of inputs that trigger these edge cases. You'll probably be running this random generation for a really long time. But it's actually a very good idea. And so people have tried to iterate on this in the past and say, how can we make this more practical? Like how can we take this random generation idea, but somehow generate the right cases that make our programs do funny things? And this is a technique called fuzzing. So fuzzing is just the practice of like running your program a lot of times with a bunch of different inputs in order to find inputs that cause it to crash. And the most common kind of fuzzing, there's what's called blind fuzzing, which is actually exactly what you suggested, which is to just blindly throw random inputs at your program. But the most common kind of fuzzing that's actually practical is called coverage-guided fuzzing. And let me show you how this works. So with coverage-guided fuzzing, you take a normal input to your program, something that you would normally come up with, and you run it through your program and watch what it does. So this thing is called a control flow graph. Don't worry about the fancy terminology. It just means like watch where your program goes. It starts at the beginning, it goes through this if statement, and then it goes through this for loop 5 times, and then it calls this function, and then it calls this function, and then it returns back to main, and then it returns out. That's like the path that it took to your program. It went through this if statement, this function, blah, blah, blah. And you just write that down. You say, okay, this is what my program did. It went through this sequence of operations. Now let's try to take this input and mutate it. We're going to just change it a bunch of times to come up with a bunch more inputs that I don't know, some of them have a character flipped, some of them have extra characters added, some of them have extra characters deleted. We just modify it a bunch of times. And then we run each one of these inputs through our program and observe what these do. And many times, nothing interesting will happen. Like for these two inputs, maybe they do the exact same path as before. You know, it goes through the same if statement, calls the same function, which calls the other function again, which returns back to main, and we saw the same thing happen. The data might have been different, right? Because we did supply a different input. But take this uppercase string example. If you provide a different string of the same length, it will actually take the same path, even though it's different data. Like it's going to loop the same number of times. It's just going to convert those characters to uppercase, and then it's going to print it out, and nothing bad happens. But maybe, just maybe, with some of these, like one or two of these things that we tried, maybe we see, we actually ended up with different behavior here. We took the else instead of the if, or we called a different function, or something different happened, like our program went a different way. So we're going to throw these out because our program did pretty much the same thing and is not very useful. But we're going to keep these two inputs, and we're going to try mutating those. And we're going to see if, we took a different path here. Maybe we can take a similar path, but maybe get to some other function that we haven't seen before, that wasn't called before. And you're trying to work your way to the edge cases, right? In edge cases where some code runs that usually doesn't run. You have an if statement that handles something rare that usually doesn't happen, or these kinds of rare cases, and you're trying to work your way closer and closer to those. You're saying, okay, well, I got new behavior here. Can I tweak this so that at some point here we end up seeing something else that's different? And you do this again, and most of the time the behavior is the same, but occasionally, you discover some new control flow path, and then you keep this and you continue forever. And somebody asked, like, can you get any guarantees from running sanitizers? Fuzzing helps because it helps you to discover weird inputs, but fuzzing does not solve the problem either, right? It's very simple in concept. It's very, very, very effective. By the way, like I think a majority of security bugs, like high profile security bugs in the last, particularly with open source software, in the last decade, have been discovered from fuzzing. Fuzzing is a very, very, very effective technique for finding bugs. Everyone should fuzz. It's not that hard, but it doesn't provide any guarantees that the program is bug-free, because this process never actually finishes, right? You're just generating more and more random inputs, and you're trying to find the right random inputs. But if your fuzzer runs for 24 hours and it didn't find anything, maybe it just didn't find the weird edge cases yet, and maybe it will if we run it for longer, or maybe there are no weird edge cases and everything runs fine. There's a project called Google Open Source Software Fuzz. They basically devoted a very large cluster of computers that just fuzz open source software 24/7. Like, that's all they do, over and over and over and over and over. And this process never ends. Like, you need to be continually fuzzing. Occasionally it finds a weird edge case that pops up somewhere. But it can't guarantee anything. If you don't find anything through fuzzing, that doesn't mean that there's nothing there. Any questions about this? Let me read through these questions. How would you integrate this in a CI/CD pipeline? I think Julio answered that. Okay, yeah. If you still have some of these questions, let's talk about these afterwards. CI is a very important development practice, but maybe we'll spend some time at the end. So this is dynamic analysis. If you find bugs through dynamic analysis, you know for sure that they're problems and you can go fix them. You don't really get false positives in dynamic analysis. Like, it observes something bad happened. You're like, okay, well, something bad happened. Let's fix it. But it can't find everything. And that's really the major shortcoming here. So, is there some way that we can just look at the code and find problems without having to come up with a specific test case to manifest that problem? And this is what static analysis is about. We just want to look at the code without running it and see if we can spot these issues. So let's play a game. Let's play the You Be the Static Analyzer game. I'm going to give you some code, and you're going to tell me if you were to write a static analyzer, like if you were to try to spot these issues, what would you do? So here we have the code from last class where, man, I'm really giving tutorial point a hard time, but it's bad code. And you want to try to help people who are writing code like this. How do you find them, or how do you help them find their issues? Like, if you were to write a program to find the issue here, what would you do? Yeah, super, super simple. Just Control F. Like, just look for the string getS. Really, it's maybe a little more complex than that, because if getS is a substring of some other function name, then maybe you don't want to flag that. But basically, that's the idea. Is like, you look for a function call to getS, and you're like, hey, that's probably not such a good idea. Maybe you shouldn't do that. And just these like very, very simple Control F kind of checks and searches can actually be extremely helpful. This is a practice called linting, which dates back to the first linter from 1978, which was named because it it traps tiny bits of fiber and fluff shed by clothing. This like program that you're running, this linter, should act like a lint trap, detecting small errors with big effects, which is exactly what it's supposed to do. You use very simple techniques to find very obvious mistakes that might have big consequences. So there's a bunch of different rules that you can employ, and there's kind of a spectrum here. There's the rules that are like, you really should never call that function. That's never a good idea. GetS is one of them. Like, there is no world in which getS is safe. And then there are rules where it's like, stylistically, you probably shouldn't do that. People who do that often end up introducing bugs. I don't know if your code is buggy, but that's probably not such a great idea. Stir copy is an example of this. Stir copy is a function that probably shouldn't be called. You can call it safely, right? So what does stir copy do? It copies one string into another buffer. And the reason that it's dangerous is because it doesn't know how large the buffer is that it's copying to. And so it can end up overflowing that buffer. You can use it safely. So if you always make sure that the buffer that you're copying to is large enough to hold the string that you're copying, then everything is fine, right? If you're copying a string that is 16 characters long, so it's really 17 bytes with a null terminator at the end, and you always make sure that your buffer is at least 17 bytes large, then there's no problem there. But you probably want to write a lint rule there saying, you probably shouldn't call stir copy because if you forget to have space for the null terminator, or if somebody changes the code around in the future and does a refactor and all of a sudden the buffer is not large enough anymore, then we're going to have problems. There are all sorts of rules like this. There are also like indentation rules and like code formatting rules. Like, okay, let's have a consistent style so that the code is easier to read. And that's the idea with linter rules. Again, just because there's an error doesn't mean your code is broken, but the errors are intended to make your code better. So some of you may have seen linters in the context of like JavaScript. They've become extremely popular there. A really good linter that you should check out for C and C++ is called Clang Tidy, which has a whole long list of checks that it can do, from simple formatting checks to it actually gets pretty advanced, and we'll talk more about that in just a moment. Yeah, Kenny. You can use them at any point. So there are a lot of IDE plugins and editor plugins that will run them like every time you save the file. And those can be really helpful for just fixing small things as you're working, so you don't have to like lose your train of thought. Some people don't really like the constant feedback from the linter. So they don't like doing that, but after they're done making some big changes, then maybe they'll run the linter and it'll find like a bunch of problems, and then you go and fix the problems. It's very common to have a linter that runs. So y'all probably haven't had a lot of exposure to version control, but when you're working on a team, there's usually what's called a version control system, like Git is the most common one, where like everyone stores their code. And when you go to work on something, then you have your own local copy. You can mess around with it, and then you push it back to this central place where everything is stored so that everyone else can see your changes. So everyone has their own local copy, and then when you are like, hey, teammate, can you review my code? Or like, okay, I made some progress. I'm going to push it back so everyone else can see it. At that point, you can set up software to like check the code and make sure that it's good before everyone else sees it. This is called a commit hook or a push hook, where like every time you try to upload your code for everyone else to see, it'll run some checks on it to make sure that it like follows the standard team style, to make sure it doesn't have any obvious mistakes. It just saves everyone some time. And it's very common to run linters at that stage too. And then obviously before you ship your code, you probably want to run some automated checks too. And that's another place where you want to run it. Clang Tidy, by the way, has an auto fixer. So for simple issues, you don't even have to fix the issue. It will just fix it for you, which is pretty nifty. Okay, so we said we have a way to find these sorts of issues. What about this? let's say that somebody writes some code like this. How do you help them find the issue? And just for the sake of time to point out the issue, this print to upper, it's just uppercasing the string and printing it. It's not particularly important. There's no mistake here. But here, what we're doing is we're reading input from the user. This is fine. And if they enter a string that is not quit, so if it's not quit, then we're going to say set this to input. To make uppercase will be our input string. But if they did enter quit, then we're not going to make this uppercase. But this code is kind of buggy, and if you type quit, then car to make uppercase ends up being null, and it calls print to upper anyways. This should really be inside of this if statement, but it's outside of the if statement for some reason. And so we have some invalid access here. We're passing an uninitialized pointer to print to upper. Does everyone see the problem? This is uninitialized. It's potentially initialized here, and then we're passing a potentially uninitialized pointer to print to upper, which then might go and access uninitialized memory, which is really bad. So what do we do? How could we write a program that could like analytically figure that out? That could just look at this code and realize, hey, this variable here might not be initialized. That's a really good suggestion. So what's a control flow graph? A control flow graph is where you trace through the possible places the program could go. So the control flow graph is really simple here. Like the program goes through line by line. It goes here to here, here, here. And then after this point, it could go into the if statement, or it could go around the if, like it could skip over this if statement. And so this is called a branch, where you could go two ways. We could go this way into the if statement, or we could go this way and skip the if statement and go directly to here. If we go into the if statement, then we run this line, and then we go to this point, and then we go to print to upper. So basically, we just look at all the ways that we could possibly go through the program, and then we can see here, is it possible that we got here, and we got here without initializing this variable? Like, did we pass an uninitialized variable here? And this technique is called Dataflow analysis, where you basically take your variables, your data, and then you just trace through the possible execution flows of the program, the possible execution paths, and keep track of what are the possible values that my variable has at this point. And so if we were to trace through this control flow graph, which is very simple, if we just trace through like where the program can go, by the way, I don't really care about the fancy terminology. If you know the terminology, cool. But if you don't feel like you have to memorize all of the stuff, because I want you to understand the limitations here conceptually. But this is not like a program analysis class. So here we have a variable. We didn't put anything inside, so it's uninitialized. That's the only possible value inside of this variable. And then we have two ways that we could go. We could skip the if statement. So if we skip the if statement, then down here, to make uppercase is still uninitialized. We didn't do anything. But if we go inside the if statement and then get to here, then it's possible that to make uppercase is our input. So before print to upper, there's two possibilities. It's uninitialized or it's our input string. And then you can look at this next line and say, hey, wait a second, you're calling print to upper, but you can't guarantee that your input is actually initialized. It could be uninitialized here, and that's problematic. And this technique is extremely powerful. There's a lot that we can do with this. Here's another maybe more complicated example, which is very, very, very common. I have written code like this. So the specifics are not important here, but basically we're calling stir dupe. What does stir dupe do? It copies a string to a new heap allocation. So stir dupe internally is calling malloc. It's returning us some memory that we are responsible for freeing. Okay, so what we're doing is we're going through this code, we're extracting some information from the code, and at the end, we're freeing the memory, and life is good. So this is very important, otherwise we have a memory leak. But while we're doing our work, it's possible that we have some errors. And if we have an error, then we bail and we say, hey, there was an error, and we return from this function. A very, very common mistake, like happens all the time in C and C++, is when you allocate some resources, but then you bail early because something bad happened and you forgot to clean up your resources. I'm sure you've written bugs like this in the past, maybe in 107. This happens in production all the time. Like there's a lot of networking code that will receive messages from the network. It allocates some memory to handle those messages, and then it's like, wait a second, there's something wrong with this message, and so it stops processing the message, but it forgets to free the extra stuff that it allocated earlier. And this stuff happens everywhere. So can you write a tool that is able to go through this code and find these kinds of mistakes? And it turns out that the same technique, Dataflow analysis, can find these sorts of issues too. So there's something called liveness analysis, which is it's the same thing. But instead of trying to figure out what values these have, it's trying to figure out when these variables are alive, like when they're actually being used. And if we get to the end and they're still alive, like if let me just walk through it and you'll see. We say that, okay, at this point, parsed is a pointer to a heap allocation. Okay? And so if we go into this if statement, parsed is still pointing to a heap allocation. And if we hit this return, then you're like, hey, wait a second, we reached the end here. Like, we're leaving. Parsed is no longer live. Like this variable is about to go out of scope, but it's still a heap allocation. It's still pointing to a variable on the heap, and you didn't free it, so that's a problem. And if you run this through clang tidy, actually, clang tidy is doing this Dataflow analysis, the same linter that I was talking about before. It will spot errors like these, which is really helpful. And it will even work even if you have multiple functions involved, because tracing function calls is not that different from tracing if statements. When you go through an if statement, it's like, okay, you could go into here, you could go some other way, somehow you get over here. Same thing with function calls. So here's a function that allocates some memory, and then we call free sometimes, which is a silly function that just generates a random number. And if the random number is 1, then it returns without freeing the memory. Otherwise, it does the right thing and frees the memory. So most of the time, this program will work fine. It will allocate some memory and then free it, and life is good. But every once in a while, if we somehow get 1 out of this random number generator, then we have a memory leak, and this memory is not freed. That's exactly right. Yeah, it's looking through the source code. It does some like transformations on the source code to make it easier to analyze. It actually looks through what's called the abstract syntax tree, but it's going through the source code, and it just goes line by line, and it's like, okay, we went here, we went here, yeah. So if we look at this program, buff is it's a pointer to a heap allocation, and then we call free sometimes. So same thing, like nothing really changed here. And then there's 2 ways we could go, right? We could go into the if statement, or we could skip the if statement. If we go into the if statement, well, buff is still a heap allocation. But if we skip the if statement, then buff is now a freed allocation. So when we return back from this function, after this point, buff is either still a heap allocation or it's a freed allocation. And then we get to the end, and you're like, hey, wait a second. It's possible that we didn't free this buffer. That's not so good. And if you run this through clang tidy, it will say, hey, you have a potential memory leak of memory pointed to by buff. You're returning here. This is the return 0 at the end. It's saying you're returning here. You allocated memory here, and potentially it was not freed. It does this exact analysis that I just showed on these slides, and it's like, I'm not convinced that free was called 100% of the time. And this is the kind of code that like would take forever for a dynamic analyzer to find, because the chances of this condition being true is so small, you probably won't see it. But maybe 1 in a million times it does happen, and here it's pretty benign. It's just a tiny memory leak of 8 bytes. But in other cases, it could be a more severe issue. Okay, so yeah. Hold that thought. That's a really good thought. Turns out the technique does not work so great with loops, particularly loops with very large bounds. Okay, so some limitations. You can get some false positives out of this. The data flow analysis is going to go through every single branch of your program, even if it's not actually possible for some condition to be true in real life. Usually it's like some combination of variables. You're like, if this is true and this is true, but actually it's not possible to get there. And it'll be like, hey, you have a problem here. And you look at the code and you're like, yeah, but that could never happen. That's impossible. And false positives are actually, it might not sound that bad. You're like, okay, well, it finds some bugs and it finds some things that are not bugs. At least I know about the bugs, right? What's so bad about having some false positives? But the thing is, if your tool has a lot of false positives, nobody's going to use your tool because they're going to be wasting so much time trying to look into the false positives, saying, is this a real issue or is this tool just tripping? And then that's not very helpful. People won't use that. So your static analyzer needs to find as many bugs as possible without flagging things that aren't actually bugs. And this turns out to be a pretty hard problem. A smaller problem is that, well, it's still a big problem. For the sake of performance, right, like large production code bases are very often millions, tens of millions, occasionally even hundreds of millions lines of code long. And if you try to analyze all of that in one shot, it can end up going really, really slow because you're like, okay, well, there's just so many possible paths that I could follow all around this code base. It's going to take a really long time to analyze. And so most static analyzers only look at one file at a time, which means that if you take this example that I showed here, if you split this into 2 different files, it won't actually find this bug. There are flags that you can use sometimes to try to like join files together or like do a cross unit analysis is what it's called. But a lot of times they only look at one file at a time. And so they won't find a lot of bugs just because they don't see the whole picture. If you're interested in this, by the way, CS243 is actually a program analysis class. So they talk a lot more there. So you look at this and you say, okay, well, I can live with those limitations, like the false positives, and we'll just build a good tool and maybe I'll add the options to analyze the whole code base at a time. Great. Let's tidy all the code. Let's find all the bugs. What's the deal? Like, what's wrong? Why doesn't that work? So let me give you some problems. This code, if you run this, it's undefined behavior. Something is undefined behavior if the argument that you pass to the program does not have the character A in it. So stir car, or however the heck you say that, it looks for this character that you provide in this string. And if the character is present, it will return the address of the character in the string. It'll say, hey, I found it at this location. Otherwise, it returns null to indicate that it didn't find it there. And so if the string that you're searching for does not have the letter A, then this is going to be null, and you're going to be printing out %s. This is going to follow a null pointer, and this is going to segfault and crash. And this is 2 lines. I can look at this and I can be like, that's a bad idea. Like that's not good. I ran this through 3 different static analyzers. I ran it through clang tidy, CPP check, which is similar to clang tidy, and scan build, which is a more this is the clang static analyzer, which is a more sophisticated analyzer. None of them found any problem with that. They're like, oh, that's cool. Looks fine to me. So what do we do? Like, how would you modify your static analyzer to fix this problem? Yeah. let's just add a rule. Let's just say, okay, well, if you call stircur or stircar, or however the heck you say it, then just make sure that you check if it's null and like don't do bad things if it's not. But okay, well, what if the program calling stircur is like it's calling it on a string that's guaranteed to have the character that you're looking for? In our case, we were looking at user input, so we don't know. Like it may or may not have the letter A in it, and so that's bad. But what if it's on like some constant or something else that they know for sure will have the letter A, and so you know for sure like this function is not going to return null. If you add this rule, that's going to raise a false positive, because you're going to have code that is like, okay, I know this character is here. I just need to find the position of it. And your linter is going to be like, oh, did you check for null? And you're like, I don't need to check for null. I know it's there for sure, 100%. And false positives are not good. And also, what about all the other functions that could potentially return null? Like, are you going to add a rule for every single function that does this? Another suggestion that you could make is, okay, well, if our static analyzer is kind of like running through the code, why can't it just see, like, why can't it just look at the code of stircur and know that like, oh, okay, it might return null. That way you don't have to write a special case for every single function that could potentially return null. And this is actually going back to Andrew's point of like, if we have a loop that loops 1,000 times and then it does something bad, like, is this static analyzer going to run all of those loops? It turns out that many of these static analyzers, when they encounter a loop with sophisticated conditions, they just bail. They're like, I don't really know. I don't know what's going to happen. And so they stop checking. And so I tried doing this. I implemented my own version of this so that in the same file, so that I could have it look through the two functions together, and it still didn't find any problems because of this while loop, where it's like looping character by character until it finds the character that you're looking for. And okay, so like even if you could fix this problem, here's a different program. So I allocate a buffer and I copy using stir and copy into this buffer. Stir and copy only copies, like there's no buffer overflow here, because we're saying copy up to 16 bytes into this buffer from our input string. So no buffer overflow, life's good, except if your input is longer than 16 bytes, it will take the first 16 characters and copy them into the buffer, and it won't null terminate the string. So it's filling the buffer with 16 bytes, no null terminator. C strings are supposed to be null terminated. Like if you're returning a string, it's supposed to be 15 characters and then a null terminator. Really what stir and copy is doing is it's returning like a sequence of characters. It's not really a string anymore because it doesn't have a null at the end. And then we're trying to print this as a string, which expects a null terminator. And this will actually print like all of your memory until it finds a null terminator somewhere. So it's not a buffer overflow in writing to the buffer, but it is a buffer overflow. You're reading past the end of the buffer because printf says, hey, let's start reading from the buffer. And so it prints a character and it prints another character and it prints another character and it just keeps going. There's no null terminator to tell printf to stop. And so it just keeps going, reading way past the end of the buffer, and it will print lots of extra memory. For those of you who heard of Heartbleed, Heartbleed was a vulnerability in OpenSSL. It's like used in web servers for HTTPS. It would actually print out, it was something similar to this, where it would print out the contents of the web server's memory by accident because of a buffer read overflow. So even though you weren't corrupting memory, even though you couldn't take control of the process, you could see all of the process's secrets, all the program's secrets. And if that web server was like a bank, then you could kind of see what everyone was doing when talking to the bank, and that was really bad. So subtle, but very not good. And we run this through our static analyzers, and they're like, oh, cool, everything's fine, no problems here. And you're like, what? How do we fix this? Well, let's just add a rule, right? Add more rules. So I'll just make sure that programs add a null terminator after calling stir and copy. If you call stir and copy, you have to make sure that you have a null after that. But what about programs that, so our program, it used stir and copy, and then it used the result as a string. Like we were expecting there to be a null terminator. But what if they don't use it as a string? What if they're not calling printf afterwards? What if after calling stir and copy, they're like, okay, I have 16 characters here. I'm going to use up to 16 characters. I don't care if there's a null terminator or not. Like, what if the code is actually fine? We don't want to introduce false positives. And are you going to track down like every single function that depends on the string having a null terminator? It's intractable to figure this out because there's just so many different ways that we can potentially mess this up. So this kind of leads us to a fundamental limitation of static analysis. Dynamic analysis, we can only see problems that actually happen when we run this thing. Static analysis, we could sometimes spot problems, but we also have no guarantees that a program is bug-free. Because if you can only look at a few lines of code, you can't really tell without broader context whether that code is safe. It's like, okay, well, we got a car star back from this function. I don't know for sure what this other function did. Like, I don't know if this car star is null or not. I don't know if it points to a string that is null terminated or not. I have a car star. I can't really tell what's inside of it without knowing what that function did. And it's hard to know what that function did without knowing what the inputs were and without actually like running the program. Like without running the program, it's hard to tell what the program is going to do. And getting that broader context, like knowing exactly what's going to happen, is not possible in the general case because of the halting problem. Like if you want to know what a sufficiently complex program does, you actually have to run it. And if you run it, then we're not doing static analysis anymore. Now we're back in dynamic analysis land. And this is really problematic. So you can always add more rules, but there will always be other ways to mess things up. And you'll add false positives, and it's just very hard. So is there some way that we can make this more tractable? Like, can we make it easier to verify small snippets of code in isolation without the context of like running the entire program and seeing what the whole program does? This is really our goal in this class. In this class, we're focused on ways to make it hard to write incorrect programs. We want it so that if you write a program that has a bug, the compiler will say, hey, that's not right. Like, and we want some guarantees on this. We want to guarantee that you can't have like memory problems. And we tried dynamic analysis, that doesn't give us any guarantees. We tried static analysis, that doesn't give us any guarantees. But is there a way that we can change the way we write our code so that we just have a small snippet of code and the compiler can look at the small snippet without context and say, that looks fine to me. It can look at some other small snippet and say, that looks fine to me. And when we put all this together, everything works fine. Like, is there a way that we can do this? I'm out of time, so I'm going to stop here and we'll pick it up on Tuesday. But it turns out that if you add just a little more information to your code about what you're expecting the code to do, if you actually express your intent to the compiler, like, hey, I'm returning a car star and I'm returning a car star that might be null. You just add that little bit of information. Then the compiler is able to take that, and anywhere that calls your function, it's like, okay, I know this function could return null. Make sure that you know how to handle that. Like everyone that uses that function, make sure that you're able to handle a null being returned, and then it can check this. We'll talk about how to actually achieve that on Tuesday, and that will bring us to Rust, which has really drawn on this, and this is why it's designed the way it is. If you have any questions, I can take any quick questions. Julio also has office hours after this, but thanks so much for coming, and I will see you all next week.